Chapter 1. How a basic graph works. A basic graph has two axes, a displacement axis and a time axis. Displacement is on a one-dimensional line and it measures the absolute distance from a point.
Okay, so we can take our trusty lab rat Boris. If Boris is standing still and we track his position through time, we can see that since he is not moving, the slope of the line will be flat. If we give Boris some velocity, we can see how his position is changing over time, so the line will have slope. The slope of the line will be directly proportional to the velocity.
Chapter 2. What is a Minkowski diagram? When graphing the effects of relativity, we use a specific type of graph known as a Minkowski diagram. A Minkowski diagram is very similar to a normal space-time diagram, but with some key differences. On a Minkowski diagram, space is on the x-axis, and time is on the y-axis. This is reversed from a classic graph. The choice to swap the horizontal and vertical axis is arbitrary, and simply originated from physicists' preference. But arbitrary or not, it is the current standard, so it's how we will show it to you. You may notice that the time axis on a Minkowski diagram is marked as ct instead of t, meaning the speed of light times time. While the speed of light times time is technically a unit of space, it's much simpler to think of it as another unit of time, since in essence it's just how far light travels in a given time. The reason for the time axis to use units of length is to have both axes use the same unit. Just as time can be measured in light years, so can space. This results in light creating a path with a slope of 1 on a Minkowski diagram. Chapter 3. How Boris sees the world.
We can see that despite the flipped axis, the behavior is basically the same, with the main difference being that the slope is now inversely proportionate to velocity. We'll cover this in more depth later, but the time position line can be thought of as the time axis for a given observer, since velocity is relative and everyone is stationary in their own reference frame.
Chapter 4. Boris turns on a flashlight. As mentioned earlier, this path of light has a slope of 1 on a Minkowski diagram. Because nothing moves faster than light, we can trace a 45-degree angle cone from any object that outlines all the spaces that it can influence in the future.
As an example, here's everything in Boris's future. And here's a few more events with their light cones shown.
Chapter 5. Boris goes relativistic. If we move the space axis along the time axis, we can see the order that events occur in a given reference frame. Therefore, we can visualize how an observer sees space by adding a space axis specific to that observer.
Using the three example events shown earlier, we can see how Boris, a stationary observer, would see the order of events as traffic, alarm, lightning. As the velocity changes, we can see how the time axis does in fact tilt to accommodate. Using the same example again, we can see how when we change Boris's velocity to shift the time axis, the order of events can change. Depending on the speed Boris is moving, he can either observe the order of events as alarm, traffic, lightning, or traffic, lightning, alarm. If we refer back to the three events light cones, we can see how the lightning event happens inside of the traffic event's light cone. Using this, we can visually see how it is impossible for Boris to see the lightning happen before the traffic event, because he would need to move faster than light for the slope to overcome the light cone.
Chapter 6: The Math Behind It.